Okay, this is Pre-ACE Chemistry Section 2.2 on separating and purifying substances. We'll go through this pretty quickly, but highlight some important aspects. So, types of substances to separate. There is the solid from liquid. You did that in the first lab by separating the lime from the lime water. So not all the lime was dissolved in the water, so we used a filtration system to help separate the solids from the liquids. You have immiscible liquids, which basically means they are they don't mix. We have like example of oil and water. Solids, you can use a magnet to remove iron from sulfur. Those are ways to separate. Solutions, this is an important one. So things that mix together. So for example, vinegar and water are mixed together. They will dissolve into each other and you can't tell that they're a solution. So solids from liquids, you can decant. This just means you pour off the liquid. This is useful if the solution is settled all the way down and you don't need all the liquid off. So for example, you can use a example like that. You can see the liquid is above the solid, and again, you don't need all the liquid, so it's useful and it's quick. Filtration you did before. You used a funnel. It's called a Hirsch funnel, a Buchner funnel, and you use a vacuum to remove the pressure, and you got the liquid all the way on the bottom and the solid on top. You can use a centrifuge. High-speed RPMs allows you to separate very small parts of solids, almost like orange juice. If you want to put that in a centrifuge, you can separate the liquid from the pulp. It looks like that machine. Alright, immiscible liquids, they don't mix. So oil and water, different polarities. Oil is nonpolar, water is polar, so they aren't going to mix. Usually this is very easily by using a separatory funnel, just letting them separate by themselves, and then you can either decant or use different separation techniques. So for example, you have to let it sit and let the oil go to the top, and you can separate. So water polar, vinegar is polar, non-polar is like oil, like gasoline, which is from oil. Mixture of solids, based on density, you can separate. For example, sand and gold, they're going to be different based on their densities. Will separate. Use magnetic properties. So, like first example, you can use a magnet from iron to remove from sulfur. And then sometimes you can use solubility properties. So if you have like salt and iron, you can dissolve the salt in water and leaves you with a solid of iron. Alright, this one is very important because a lot of times you have solutions, things that mix. So distillation, they separate by using different boiling points. The lower boiling point liquid will evaporate sooner and then condense back into pure liquid. When boiling points are not similar, so you have to make sure that the boiling points are quite different, within 10 degrees of each other. They're fine, but anything less than that, you want to make sure you use a different technique. So this is what a distillation kit looks like. You see that you're heating the liquid up here and you're cooling it, in this apparatus is called a condenser, back into a liquid form. So it separates into two different liquids. It could be used also to separate solutions that like salt water. So sometimes you're left with just the salt or the solid on the bottom or in the flask, and just left with water in the condenser. Cold water in, cold water out. That helps condense the vapor back into liquid. Here is another type of distillation called fractional distillation. He talked about a brief introduction to this in chapter 1, but a fraction column is used to help with more purifying the liquid. So you have different layers, so it takes more and more energy to get to a pure substance, but you get a pure substance at the end. So you use this when boiling points are very similar, so when they're less than 10 degrees, and this achieves a better separation. So that's the fractional column. Chromatography is used to separate solutions as well. You see this a lot. They travel different distances based on their molecular weight. So you can see this, use this sometimes with ink is a good example, or food coloring. Based on its traveling of the color, it travels different distances. So substances can be divided by their RF value. Every substance has a specific RF value. So if you can measure its RF value, you know what substance was present in the solution. It's a really simple calculation. You just take the distance from the center of the substance divided by the distance the solvent traveled, and you get a value. So for example, the substance traveled 2.1 centimeters here, and the solvent, usually like ethanol or water, traveled 2.8. So the fraction RF value is 0.75. Here's another example. We have blue and yellow. They travel at 3.1 and 5.8 respectively, and the total distance the solvent travels was 8.5. So you get two different RF values, one for yellow, one for blue. Alright, solubility. So solubility is a solution. It's made up of a solid and a liquid. Usually the solid is called a solute. So for example, salt, and the solvent, generally water, is the liquid. So if something is soluble, that means they will dissolve in that liquid. So salt, sugar will all dissolve in water, so they're soluble in water. So when you mix it, they will all dissolve, and you really can't tell it you have a solution just based on how you remember what you put in there. Insoluble means that the solid will not dissolve. So like sand and water won't dissolve, so you're stuck with just sandy water, as you can see here. Solubility is measured in how many grams of the solid or solute and per how many 100 grams of water. So it's always measured at 100 grams of water, and then the more something you can dissolve, the higher the grams of solute. Here is a solubility curve. So you can see that solubility is a factor of temperature. Most things are going to rise up as temperature increases. So you can see here, sodium chloride, the blue here, travels pretty low. Doesn't really that much temperature independent. But if you look at potassium nitrate, this green one, you can see a really rise spike as temperature increases. And there are some cases that actually is opposite, like cerium sulfate actually decreases with increased temperature. So solids increase temp, more solid dissolves, like you see here in KCl. A saturated solution is the amount of solid that you can maximize at that certain temperature. So that's what the saturation line is located. So the saturation line is exactly what the line is on the graph. A unsaturated solution means you can increase the solute, so it's going to be below the saturation line. And then supersaturated is the point where there's more solute dissolved than possible to hold, and that is going to be above the saturation point. So how do we increase solubility? We can agitate it. That means stirring. And that solubility of gases. Gases are opposite to solids. Gases are always going to be less soluble at high temperatures. This is pretty easy to remember because if you were to leave a Coke bottle in a hot car, you will notice it turns flat. That's because the CO2 escaped, because it's not soluble at high temperatures, so it's going to leave the solution and escape into the environment. So gases become less soluble at high temperatures and will become flat. Soda becomes flat at warmer temperatures, which makes sense. And if you agitate it, so what happens if you shake a bottle? You explode a CO2, so you actually have decreased solubility as well. So it's opposite of solids. In solids, you increase this agitation, you will increase the solubility. All right, so that is